Welcome to Chapter 1 of our Chemical Engineering Heat Transfer series, Conduction, Convection, and the Overall Coefficient. The subtitle tells you where we are going: Fourier's law, film coefficients, and thermal resistances in series. This chapter opens the series with the two mechanisms that carry almost every duty in a plant: conduction through solids and convection at surfaces, and shows how they combine into the single number every exchanger is sized with. The overall heat transfer coefficient Our introduction series set out transport phenomena as one table with 3 rows: momentum, heat, and mass, each an instance of the same sentence. Flux equals coefficient times driving force. The fluid mechanics series developed the momentum row, where the driving force is a velocity gradient and the coefficient is viscosity. This series develops the heat row. Across these 10 slides, you will learn to apply Fourier's law, quote thermal conductivities across the metal-to-gas range, explain why the film coefficient is not a material property, combine resistances in series into an overall coefficient, identify the controlling resistance, and describe fouling as a resistance that grows. Heat transfer is a row of the transport table, and it obeys the same sentence as the momentum row. Flux equals coefficient times driving force. In the momentum row, the driving force is a velocity gradient and the coefficient is viscosity. Here the driving force is a temperature difference, and the coefficients are the subject of this chapter. The commercial reason to care is already on the table. Our thermodynamics series showed that a distillation column's reboiler and condenser are usually the largest utility consumers on a flowsheet, because every pass of reflux must be boiled again and condensed again. Thermodynamics tells you how much energy that costs, Q equals delta H, and stops there. It never says how large the exchanger must be, or whether a fouled tube bundle will still make duty in August. Those are heat transfer questions, and nearly all of them root through one equation. Q equals U a delta T duty in watts, area in square meters, a representative temperature difference in Kelvin, and U carrying everything about the materials, the fluids, and the flow. Conduction is heat moving through matter without the matter moving, energy handed between neighboring molecules, and in metals, carried by free electrons. Its law is the direct analog of Newton's law of viscosity. Q equals minus K times dt by dx. The minus sign is bookkeeping, not physics. It says heat flows down the gradient, from hot toward cold. For a flat wall of thickness L at steady state, that integrates to Q equals K a delta T over L. Thin walls and conductive materials transfer well. Thick, insulating ones do not. What makes the result useful is the enormous spread in K as typical values near 20 degrees Celsius. Copper is about 400 watts per meter Kelvin, carbon steel about 45, stainless steel about 15, water about 0.6, mineral wool insulation about 0.04, and still air about 0.026. Read them as ratios. Copper to still air is a factor of roughly 15,000. Metals conduct, gases insulate. And insulation works by immobilizing a gas, trapping air in pockets too small to circulate, so compress it or soak it, and it stops working. Convection is heat carried between a surface and a moving fluid, and it is where most of the resistance in a real exchanger lies. Newton's law of cooling is deliberately simple. Q equals H a delta T, with delta T the difference between the surface and the bulk fluid. The simplicity hides the difficulty. Thermal conductivity is a property, the film coefficient is not. The same water against the same steel gives a different H if you change the velocity or the flow regime. The picture that makes it intuitive is the film the coefficient is named for. No slip holds the fluid still at the wall, so a thin, slow-moving layer clings there, and heat must cross it by conduction through a fluid. Anything that thins the film raises H. Turbulence does exactly that, so H tracks the Reynolds number, and doubling tube velocity buys about 74% more film coefficient. As typical order of magnitude ranges, free convection in gases gives 5 to 25, forced convection in gases 25 to 250, forced convection in liquids 100 to 10,000, and boiling or condensing 2,500 to 100,000 watts per square meter Kelvin. Heat crossing an exchanger wall makes 3 trips in sequence: through the hot fluids film, through the metal, and through the cold fluids film. Sequential steps mean resistances in series, exactly as in an electrical circuit, where temperature difference plays the role of voltage and heat flow the role of current. That analogy imports a habit. The same heat crosses every layer, so the largest thermal resistance takes the largest share of the temperature difference. Adding them gives 1 over U equals 1 over HI, plus L over K, plus 1 over HO. Each term has units of square meters Kelvin per watt. This is the plane wall form. Tube curvature corrections are set aside here, since they change the numbers by a few %. Take cooling water inside a tube at 1000, a 5 mm carbon steel wall with K of 45, and a process liquid outside at 2000. The sum is 0.001 plus 0.000111 plus 0.0005, which is 0.001611, so U is 621 watts per square meter Kelvin. The wall is only 6.9% of that. The two thin films own 93% between them. Now change one thing. Replace the outside liquid with air at an H of 50, and U collapses from 621 to 47.4 watts per square meter Kelvin. Look at where the resistance sits. The air film is 94.7% of the total, the water film 4.7%, and the steel wall 0.5%. Now spend money on the water side, upgrading it from 1000 to 5000 with higher velocity and a better tube. U rises to 49.2, a gain of under 4%. You have bought pumping power and delivered nothing. The largest resistance controls, and improving anything else is wasted effort until the controlling resistance is dealt with. Run it the other way on the first case. Doubling the smaller resistance's coefficient, 2000 to 4000, lifts U from 621 to 735, an 18% gain, while doubling the dominant 1000 to 2000 lifts it to 900, a 45% gain. This single rule explains a great deal of real equipment. Whenever a gas meets a liquid across a wall, the gas is in charge. That rule has a piece of hardware attached to it. If the gas film holds nearly all the resistance, the way to improve the exchanger is to attack the gas side, and the cheapest attack is area. Air-cooled exchangers wear fins on the air side and nothing on the tube side, because area added where the coefficient is worst is the only area that helps. Fin the liquid side instead, and you have paid for metal that changes almost nothing. Look again at Q equals U. A delta TU is held down by the worst film, but the gas side surface can be multiplied several-fold, and UA, the product that actually sets the duty, rises accordingly. That is why a plain tube gas cooler that underperforms is usually a candidate for a finned bundle rather than for polishing the water side. As typical ranges, a gas in forced convection gives roughly 25 to 250 watts per square meter Kelvin, while water gives 1000 or more, so the comparison is rarely close. Fins are the answer to a controlling gas film, not a general upgrade. Everything so far assumed clean metal. Real surfaces accumulate deposits, scale from hard cooling water, biological films, corrosion product, coke, polymer, precipitated salts. Each deposit is a thin layer of low-conductivity material sitting exactly where the heat has to cross, so it enters the sum as one more term on each side. These are the fouling factors, RF in square meters Kelvin per watt, a design allowance for dirt the exchanger is expected to collect between cleanings. Typical published allowances run about 0.0001 to 0.0004 for clean services such as treated cooling water or condensing steam, and rise towards 0.001 and beyond for fouling-prone duties. Take them as order of magnitude design allowances, not measurements. Small numbers, large consequences. Add a modest 0.0002 to each side of the worked example, and 1 over U goes from 0.001611 to 0.002011. So U falls from 621 to 497 watts per square meter Kelvin, a loss of 20% bought before the unit ever runs. And an over-generous allowance is its own hazard. A badly oversized unit runs at low velocity, and low velocity fouls faster. Fouling is also the one resistance that changes with time, which makes it observable. Flows and temperatures are measured continuously, so U can be back-calculated from Q equals U a delta T and trended over weeks and months. That trend is worth reading carefully. A steadily falling U is a cleaning schedule righting itself. The surface is dirtying at a rate you can now extrapolate toward the next shutdown. An abrupt drop is usually a different fault altogether, a bypass, a blocked pass, or a leaking tube, and treating it as fouling wastes a cleaning. This is exactly the soft sensor logic of our introduction series. Infer a hard-to-measure condition, hear the state of a surface no one can see, from cheap measurements you already have. Notice what it costs. No new instrument is installed. The flow meters and thermocouples are already there for control, and the only addition is the arithmetic. That is the pattern process informatics keeps returning to, and a trended U is one of its clearest examples. Let's pull the chapter together. Heat transfer is a row of the transport table. Flux equals coefficient times driving force, and it turns the thermodynamic duty into hardware through Q equals U a delta T. Fourier's law gives Q equals K a delta T over L through a slab, and typical conductivities span copper at about 400 down to still air at about 0.026 watts per meter Kelvin, roughly 15,000-fold, while insulation works by trapping air. The film coefficient H is not a property, but a result of the flow. With typical ranges from 5 to 25 for free convection in gases, up to 2,500 to 100,000 for boiling and condensing. Resistances add in series. 1 over U equals 1 over Hi plus L over K plus 1 over H, O. The worked case sums to 0.001611 and gives 621 watts per square meter Kelvin, with the steel wall only 6.9%. With air outside, U falls to 47.4 and the air film is 94.7%. Typical fouling allowances run 0.0001 to 0.001. Adding 0.0002 per side drops 621 to 497. Next chapter, heat exchangers and the log mean temperature difference. Welcome to Chapter 2 of our Chemical Engineering Heat Transfer Series, Heat Exchangers and the LMTD. The subtitle is Sizing the Workhorse of Process Heat. Chapter 1 built the overall heat transfer coefficient U, the single number that collects film resistances, wall conduction, and fouling. This chapter spends it. Given two streams and a duty, how large an exchanger do you buy? The sizing equation is the same transport law in the same form, but the temperature difference now has to be made precise, because in a real exchanger it changes from end to end as both streams heat and cool. Across these 10 slides, you will learn what a heat exchanger does for a flow sheet and why heat integration pays twice, why shell and tube remains the industry standard, why countercurrent flow beats cocurrent, how to compute the log mean temperature difference, and why the mean is logarithmic, how to size a unit end-to-end including fouling and the F correction, and when to reach for the effectiveness NTU method instead. A heat exchanger moves heat from one stream to another without mixing them. Stated that plainly, it sounds like plumbing, but the economics are not plumbing at all. Every hot stream that needs cooling is a stream someone is paying cooling water to quench, and every cold stream that needs heating is steam on the utility bill. Match the two, and one piece of equipment deletes both charges at once. That is heat integration, and our introduction series gave it systematic form. Pinch analysis, which computes the minimum possible hot and cold utility before any network is drawn. Exchangers are the hardware that realizes those targets. The equipment that does most of this work is the shell and tube exchanger. A bundle of tubes carrying one fluid, sealed into a cylindrical shell carrying the other, with baffles forcing the outside stream to zigzag over the tubes. It has been the standard for a century for unglamorous reasons. It tolerates essentially any pressure and temperature you can afford the metal for, it is mechanically robust, the bundle can be pulled for cleaning, and its design is codified by the TAMA standards. The two streams can run the same direction or opposite directions, and the choice is not cosmetic. In co-current or parallel flow, both enter at the same end. The temperature difference starts large, hot inlet against cold inlet and collapses as the two streams converge toward a common intermediate temperature. In countercurrent flow, they enter at opposite ends, so the hot inlet faces the cold outlet and the hot outlet faces the cold inlet, and the difference decays far more slowly. It is exactly constant only when the two capacity rates match. The decisive row is the third one. Co-current flow can never lift the cold stream above the hot stream's exit temperature. The two approach each other from the same starting point, and once they meet, heat stops flowing. Countercurrent has no such limit, and the cold stream can leave hotter than the hot stream leaves, a temperature cross that is simply unavailable in co-current. It also needs less area for a given duty and spreads the tube wall gradient out, which is why it is the default arrangement, and why everything that follows assumes it. The sizing equation is Q equals U times the log mean temperature difference, and the trouble is that the driving force is not one number. It varies continuously along the exchanger, so what average is correct? Not the arithmetic one. As heat crosses the wall, each stream's temperature changes in proportion to the heat it has absorbed or given up, so the gap between them changes exponentially with area rather than linearly. Integrating along a countercurrent exchanger, with constant U, constant specific heats, and negligible heat loss to the surroundings, gives the log mean. Delta T1 minus delta T2 divided by the natural log of delta T1 over delta T2. Pair each end correctly. Hot water cooling from 90 to 50 degrees Celsius against cold water heated from 20 to 40 gives delta T1 of 50 Kelvin and delta T2 of 30 Kelvin. The log mean is 20 over 0.5108, which is 39.2 Kelvin. The arithmetic mean of 40 overestimates it by about 2.2%, and that gap widens as the ends become unequal. Sizing runs in a fixed order: duty first, then driving force, then area. The duty comes from an energy balance on one stream, not from anything about the exchanger. Take 2 kilograms per second of water cooled by 40 Kelvin, with a specific heat of 4.18 kilojoules per kilogram Kelvin. Q equals mass flow times specific heat times temperature change, which is 2 times 4.18 times 40, or 334.4 kilowatts. Notice what that number does and does not contain. It is fixed entirely by the process requirement, the flow you have, and the cooling you need, and it would be the same whatever equipment you chose. The exchanger has not entered yet. That is what makes this step safe ground. Get the duty wrong and everything after it is wrong, but the duty itself is arithmetic from a stream balance. Keep the units straight as well. The specific heat here is in kilojoules, so the duty comes out in kilowatts, and the sizing step that follows needs it in watts, 334,400. Now the exchanger enters. Rearranging Q equals U a delta T log mean gives area equals duty divided by U times the log mean. We have the duty, 334.4 kilowatts, or 334,400 watts, and the driving force, 39.2 Kelvin. The missing piece is U, and for a water-to-water shell-end tube unit, a typical clean overall coefficient is around 500 watts per square meter Kelvin. Substituting, the area is 334,400 divided by 500 times 39.2, which is 17.1 square meters. That is a real, orderable number, and it took 3 lines. But note the word typical. The 500 is an estimate, not a measurement, and it is a clean value, which is why Chapter 1 spent so long on building you honestly. 2 reality checks stand between 17.1 square meters and a purchase order. Fouling, because U degrades in service and multipass geometry, because a real shell-end tube unit rarely runs pure countercurrent. The next slides take both in turn. Hold the duty and the driving force fixed and sweep U to see what that estimate is worth. At 300 watts per square meter Kelvin, the area needed is 28.5 square meters. At 500, it is 17.1. At 800, it is 10.7. Area is inversely proportional to U, so a fouled unit at 300 needs 2/3 more steel than the clean case, while a high-performance surface at 800 needs only 10.7 square meters. Uncertainty in U propagates directly into the capital cost, which is why the coefficient estimate of Chapter 1 deserves the caret got. The driving force behaves the same way, and that is where the designer has a lever. Chase a tighter approach between the streams, recover more heat, and shave the utility bill, and the log mean shrinks while the area needed climbs toward infinity as the approach goes to zero. Heat recovery is therefore never free. It is bought with metal. Common practice settles the argument with a minimum approach temperature, typically around 10 Kelvin for liquid duties, which is precisely the parameter pinch analysis takes as its input. Two corrections separate a clean calculation from a purchase order. First, fouling. The 500 watts per square meter Kelvin was a clean value. In service, scale, biofilm, and corrosion products add the fouling resistances of Chapter 1, and U falls, often by 1/3 or more on cooling water duty. An exchanger sized exactly for the clean case meets its duty on commissioning day and misses it thereafter, so designers add a fouling allowance, effectively sizing for the dirty U-second geometry. Real shell-end tube units rarely run pure countercurrent. A multipass exchanger routes the tube fluid up and back through the shell more than once, for velocity and for compactness, and some of those passes then run co-current, degrading the driving force. The standard fix is a correction factor F, a dimensionless number less than one read from published charts for the given pass arrangement, giving Q equals U a F delta T log mean, where the log mean is still the countercurrent one that F then discounts. Designers keep F above roughly 0.8. Below that, the answer is more shells in series. The sizing above worked because all 4 terminal temperatures were known. Often they are not. Asked instead, I have this exchanger and these 2 inlet streams, what comes out? The LMTD method stalls. The log mean needs the outlets, and the outlets need the duty. You guess, solve, and iterate. The effectiveness NTU method removes the iteration by rephrasing the question. Effectiveness, epsilon, is the actual duty divided by the thermodynamically maximum duty, what an infinitely large countercurrent exchanger would transfer, limited by the stream with the smaller heat capacity rate. The number of transfer units is the exchanger's dimensionless size, UA divided by that same minimum capacity rate. For each flow arrangement, there is a known relation between epsilon, NTU, and the capacity rate ratio, the smaller capacity rate divided by the larger. Compute NTU and that ratio, read off epsilon, and the outlets follow in one pass. Epsilon is also a performance score. A unit at 0.9 is already extracting 90% of the available heat, and doubling its area will not find much more. Let's pull the chapter together. A heat exchanger transfers heat between streams without mixing them, and matching hot and cold process streams cuts the steam bill and the cooling water bill at the same time. Shell-end tube is the workhorse under standard practice. Any pressure, mechanically robust, cleanable, standardized by TEMA. Countercurrent beats co-current because it maintains the driving force and permits a temperature cross. The correct average driving force is the log mean. For 90 to 50 degrees against 20 to 40, delta T1 is 50 Kelvin, delta T2 is 30, and the log mean is 20 over 0.5108, or 39.2 Kelvin, against an arithmetic mean of 40 that overestimates by 2.2%. For sizing, the duty is 2 times 4.18 times 40, or 334.4 kilowatts, and the area is 334,400 over 500 times 39.2, or 17.1 square meters at a typical U of 500. Area scales as 1 over U, 28.5 at 300 and 10.7 at 800. Then add a fouling allowance and a correction factor F, kept above about 0.8. Next chapter, boiling, condensation, and evaporators. Welcome to Chapter 3 of our Chemical Engineering Heat Transfer series, Boiling, Condensation, and Evaporators. The subtitle tells you where we are going. Phase change, the best and most dangerous heat transfer a process engineer can buy. The first 2 chapters moved heat into and out of fluids that stayed liquid or stayed gas. Let those fluids change phase, and both the coefficients and the hazards jump by an order of magnitude. Boiling is the finest heat transfer available, right up to the point where it fails catastrophically. Across these 10 slides, you will learn why latent heat, not sensible heat, sets the size of reboilers, condensers, and evaporators, how to read the boiling curve and locate nucleate boiling, the critical heat flux, and film boiling on it, why burnout is a hazard specific to constant heat flux equipment, what separates film-wise from drop-wise condensation, and why non-condensable gases cripple a condenser, how steam economy works in a multiple effect evaporator, and which parts of that result are idealized, and why a reboiler is simply a boiling exchanger with 2 classic failure modes. Water's specific heat is about 4.18 kilojoules per kilogram Kelvin. Its latent heat of vaporization at 100 degrees Celsius and 1 atmosphere is about 2257 kilojoules per kilogram. Divide one by the other and the ratio is a temperature. 2257 divided by 4.18 is about 540 Kelvin. Condensing 1 kilogram of steam releases as much energy as cooling 1 kilogram of liquid water through 540 Kelvin, a swing no liquid water could survive. Phase change is where the energy is. It is also where the coefficient is. Chapter 1, put gases at single digits to a few hundred watts per square meter Kelvin, and single-phase liquids up to about 10,000. Boiling and condensing water span roughly 2,500 to 100,000 watts per square meter Kelvin, typical design magnitudes, not constants. 2 mechanisms explain the leap. Bubbles growing and detaching stir the boundary layer that otherwise insulates the wall, and condensing vapor gives up its latent heat at constant temperature, holding the driving force at its maximum along the whole surface. So the phase-changing side adds almost no resistance, and the other side, or the fouling layer, controls the exchanger. Immerse a heated surface in a pool of saturated liquid and slowly raise the wall above the saturation temperature. That difference, the wall superheat, is the driving force, and the heat flux is the response. Plot one against the other and you have the boiling curve, which is not monotonic, and that is the entire point. At low superheat, nothing boils. Liquid warms, rises, and circulates by natural convection alone. Raise the superheat a few Kelvin and bubbles nucleate at scratches and cavities in the surface, grow, and detach. This is nucleate boiling, the sweet spot, because every departing bubble drags cold bulk liquid onto the wall, so the flux climbs steeply for a modest rise in superheat. The climb ends. Once bubbles are numerous enough to merge into sheets, fresh liquid can no longer reach the surface between them, and the curve turns over at the critical heat flux. Past the peak lies transition boiling, where vapor patches form and collapse and the flux actually falls as superheat rises. Beyond it lies film boiling, a continuous vapor blanket. Vapor conducts poorly, so heat transfer collapses. Whether that collapse is survivable depends on what is being controlled. A steam-heated exchanger controls wall temperature, roughly the condensing steam temperature. Past the critical heat flux, the flux simply drops, the equipment underperforms, and an operator notices. A fired heater tube, an electric immersion heater, or a nuclear fuel rod controls heat flux instead. The burner keeps firing and the current keeps flowing, regardless of what the surface is doing. When such a device exceeds the critical heat flux, the only free variable left is wall temperature, and it leaps hundreds of Kelvin in seconds to force the same flux through an insulating vapor film. That is burnout, melted hardware. For water at 1 atmosphere, the standard textbook magnitude of the critical heat flux is about 1 megawatt per square meter. Treat it as an order of magnitude anchor, not a design number. The design rule is blunt. In constant heat flux service, stay well inside nucleate boiling with a margin to the critical heat flux. Constant temperature devices are self-limiting, which is exactly why steam heating is the safer utility. Condensation runs the same physics backward. In filmwise condensation, the liquid wets the surface and drains as a continuous film. That film is the resistance, because every joule must conduct through it, and it thickens down the tube. In dropwise condensation, the surface is non-wetting, so droplets form, grow, and roll off, repeatedly exposing bare metal, and the coefficient is several times higher. Dropwise is not a design basis. Sustaining it needs promoters or coatings that erode, oxidize, or wash away over weeks to months, after which the surface reverts to filmwise. Standard practice is therefore to design filmwise and treat dropwise behavior as an unbooked bonus. Steam condenser coefficients quoted for design fall around 5,000 to 15,000 watts per square meter Kelvin, typical magnitudes, sensitive to geometry and condensate loading. One contaminant destroys all of this: non-condensable gases, meaning anything that will not condense at operating conditions. Only the vapor condenses, so they build up in a stagnant layer through which incoming vapor must diffuse, and diffusion is slow. A few percent of air by volume can cut a condenser's coefficient severalfold, hence the vent on every condenser. An evaporator concentrates a solution by boiling water out of it, and it is both previous sections in one shell, steam condensing on one side, process liquor boiling on the other, separated by a tube wall. With feed entering at its boiling point, there is no sensible term and the duty is latent alone. Q equals m dot times lambda, with m dot the evaporation rate and lambda the latent heat. The economics reduce to 1 ratio. Steam economy is kilograms of vapor evaporated per kilogram of live steam consumed. A single effect evaporator condenses 1 kilogram of steam to evaporate roughly 1 kilogram of water, so economy is about 1. That is an idealization, resting on the 2 latent heats being nearly equal and ignoring losses and feed preheating. The improvement is to use that vapor twice, since it still carries essentially all the latent heat that made it. Chain N effects at successively lower pressures, and, idealized, economy approaches N real economies fall short of N any per effect derating factor in a textbook illustration, is an assumption, not a measured constant, and not a number for sizing equipment. Follow the train. Live steam heats effect 1, held at the highest pressure. The vapor boiled off in effect 1 still carries essentially all the latent heat that made it, so it heats effect 2, held at a lower pressure. Its liquor therefore boils at a lower temperature, because saturation temperature follows pressure, a result from Chapter 3 of our thermodynamics series. Effect 2's vapor heats effect 3 at lower pressure still, and the last effect exhausts to a condenser. Dilute feed enters effect 1 and concentrated product leaves effect 3. Idealized, 3 effects give an economy near 3. The catch is capital. Split the available temperature difference evenly among n effects, and each gets 1/nth of it while carrying 1/nth of the duty, so each needs about the same area as a single effect unit. Total area grows roughly with n, while steam falls as 1 over n, so trains commonly settle at 2 to 6 effects. A different route upgrades the vapor instead of cascading it. Mechanical vapor recompression compresses it until it can heat its own effect, buying a similar saving with a little shaft work. Every distillation column ends in a boiling exchanger. The reboiler vaporizes liquid at the column base to generate the vapor traffic that reflux demands, and it is usually the largest single item on the plant's energy bill. 2 configurations dominate. A kettle reboiler submerges a tube bundle in a liquid pool inside an oversized shell and boils into the vapor space above. Simple, tolerant, and high vaporization per pass. A thermosiphon reboiler lets boiling lower the fluid's density and drive circulation from the column sump. No pump, less holdup, gentler on heat-sensitive material. Two failure modes recur. Fouling deposits a low conductivity layer that raises the wall temperature needed for a given duty, which degrades the product it bakes onto the tube, a self-accelerating loop. Film boiling follows when the temperature difference is pushed too far, typically by raising steam pressure to compensate for fouling. Duty then falls as the temperature difference rises, and adding more steam makes it worse. Fluid mechanics sets the last constraint. Bottom's product leaves at its boiling point, a permanent net positive suction head risk, which is why column sumps sit high above their pumps. Let us put numbers on an evaporator. It must vaporize 1,000 kilograms per hour of water at 1 atmosphere from a feed already at its boiling point. Take lambda as 2257 kilojoules per kilogram. Duty is m dot times lambda with units reconciled from kilograms per hour to kilograms per second. So Q equals 1,000 times 2257 divided by 3,600, which is 626.9 kilowatts. Call it 627 kilowatts. Because the feed enters at its boiling point, there is no sensible term. All of it is latent. Now size the surface using Chapter 1. With an overall coefficient of 2,500 watts per square meter Kelvin and a temperature difference of 15 Kelvin, area equals Q divided by U delta T, which is 626,900 divided by 2,500 times 15, or 16.7 square meters. Now suppose the steam supply degrades and the difference falls to 10 Kelvin. The same duty then needs 25.1 square meters, 50% more surface for the same job. Area is inversely proportional to temperature difference, which is why losing driving force is expensive and why multiple effect trains pay for their steam savings in steel. Let us pull the chapter together. Latent heat dwarfs sensible heat. Water's 2257 kilojoules per kilogram equals 4.18 kilojoules per kilogram Kelvin applied over 540 Kelvin, which is why phase change equipment carries the plant's largest duties. Boiling and condensing coefficients reach 2,500 to 100,000 watts per square meter Kelvin as typical magnitudes, so the phase-changing side rarely controls the overall coefficient. The boiling curve runs natural convection, nucleate boiling, critical heat flux, transition, and film boiling, with water at 1 atmosphere peaking near 1 megawatt per square meter as a textbook magnitude. Burnout is a constant heat flux hazard, so design with margin inside nucleate boiling. Condensers are designed film-wise because drop-wise promoters degrade in service, and non-condensables force vapor to diffuse through them, hence vents and ejectors. Steam economy is kilograms of vapor per kilogram of steam, about 1 for a single effect, approaching N for N effects idealized, less in practice. Reboilers are boiling exchangers, kettle or thermosiphon, killed by fouling and the film boiling it provokes. Next chapter, radiation and furnaces, the mechanism that needs no medium at all and scales with the 4th power of absolute temperature. Welcome to Chapter 4 of our Chemical Engineering Heat Transfer series, Radiation and Furnaces. The subtitle tells you what makes this mechanism different: heat that needs no medium. This chapter takes up the 3rd mechanism of heat transfer, the one that needs no material to travel through. Radiation is a rounding error on a warm pipe and the whole design basis of a fired heater, and the temperature at which it switches from one to the other is the story here. Across these 10 slides, you will learn why radiation, unlike conduction and convection, crosses a vacuum, how to apply the Stefan-Boltzmann law, and why the temperature in it must be absolute, what typical emissivities look like, and how to use them to estimate net exchange with the surroundings, how to judge from a surface temperature whether radiation is negligible, comparable, or dominant, what the radiant and convection sections of a process-fired heater each do and what limits them, and what view factor and tube skin temperature govern. Chapter 1 built the overall heat transfer coefficient out of 2 mechanisms. Conduction passes energy along through a material, molecule to neighboring molecule. Convection carries it away in moving fluid. Both need something to be there. Take the matter away and both stop. Radiation does not stop. Every surface above absolute zero emits energy as electromagnetic waves, and those waves travel perfectly well through nothing at all. The proof arrives every morning. Sunlight crosses 150 million kilometers of vacuum to warm a rooftop, with no medium at any point along the way. Nothing conducts across that gap, and nothing convects across it, yet roughly a kilowatt per square meter arrives. The awkward part for the practicing engineer is that radiation is always present and almost never important, until suddenly it is everything. A vessel wall at 60 degrees Celsius radiates, but next to the convection stripping heat off the same wall, the radiant contribution is a modest correction. Inside a fired heater at 1,200 degrees Celsius, the ranking inverts completely. Radiation delivers most of the duty and convection is the afterthought. The emissive power of a surface, meaning the energy it radiates per unit area per unit time in watts per square meter, is E equals epsilon sigma T to the fourth. Sigma is the Stefan-Boltzmann constant, 5.67 times 10 to the minus 8 watts per square meter Kelvin to the fourth. Epsilon is the surface's emissivity, a number between 0 and 1 measuring how good a radiator the surface is, and we take it up in detail on the next few slides. T is the surface's absolute temperature in Kelvin. One warning on notation: this epsilon is emissivity, unrelated to the exchanger effectiveness epsilon of Chapter 2. The symbol collision is standard in the literature, so read from context. Everything unusual about radiation lives in that exponent. Conduction and convection are linear in temperature difference. Double the driving force and you double the flux. Radiation is quartic in absolute temperature, so doubling the absolute temperature multiplies emission by 2 to the fourth, which is 16. That single fact is why radiation can be ignored around a warm tank and cannot be ignored anywhere near a flame. Work the contrast. Take a perfect emitter, a blackbody with emissivity 1, at room temperature, 300 Kelvin. E equals 5.67 times 10 to the minus 8 times 300 to the fourth, which is 459 watts per square meter. Now put the same surface in a furnace at 1000 Kelvin. E equals 5.67 times 10 to the minus 8 times 1000 to the fourth, which is 56,700 watts per square meter, or about 56.7 kilowatts per square meter. The temperature rose by a factor of 3.3. The emission rose by a factor of 123. Now the warning. The temperature in that fourth power is absolute, and there is no version of the calculation in which a Celsius value is acceptable. Substitute 300 degrees Celsius as 300 instead of 573 Kelvin, and the answer is wrong by a factor of 13. Substitute 25 degrees Celsius as 25, and the surroundings essentially vanish from the equation. Worse, a surface at 0 degrees Celsius entered as 0 radiates nothing at all, which is nonsense. It radiates 316 watts per square meter. Real surfaces are not blackbodies. Emissivity is the fraction of blackbody emission a real surface actually achieves at the same temperature, running from 0, a perfect reflector emitting nothing, to 1, a blackbody. Here are typical values, adequate for estimating and no substitute for data on the actual surface. Oxidized carbon steel is about 0.8. Refractory brick is about 0.9. Most paints of any color are about 0.9. Polished steel is around 0.1, typical. Polished aluminum or bright foil is about 0.05. Two of those deserve comment. First, oxidized steel sits near 0.8, but clean, polished steel is far lower, around 0.1, meaning a pipe's radiant loss climbs substantially during its first months in service as the surface weathers. Second, the gap between polished aluminum at 0.05 and everything else at 0.8 to 0.9 is a design tool. A low emissivity foil wrapped around insulation is not insulation in the conductive sense at all. It simply refuses to radiate, cutting the radiant term by a factor of roughly 16. Note also that visible color tells you nothing, because the emission is infrared. Now locate the crossover. Take an oxidized pipe at emissivity 0.8 losing heat to surroundings at 25 degrees Celsius, and compare its radiation against a convective estimate using a heat transfer coefficient of 10 watts per square meter Kelvin, an order of magnitude figure for natural convection to still air. Convection grows linearly with the temperature difference. Radiation grows with the fourth power of absolute temperature, so it starts below convection and overtakes it. At 150 degrees Celsius, radiation is slightly below convection, a real contribution but not the dominant one. By 300 degrees Celsius, it is 1.65 times convection, and by 600 degrees Celsius, it is 4.5 times. The crossover, where the two are equal, falls near 180 degrees Celsius on this basis. That supports a working guideline, a habit of thought rather than a law, and it is sensitive to the convective coefficient assumed. Below about 100 degrees Celsius, radiation is secondary but real. From 100 to 500 it is comparable, and neither term can be dropped. Above about 500 to 600, radiation dominates. A fired heater brings crude to distillation temperature, drives a reformer, or supplies reboiler duty too hot for steam. It burns fuel and hands the heat to process fluid inside tubes in two stages, exploiting the fact that radiation and convection dominate in different temperature ranges. The radiant section is the firebox. Refractory-lined walls with process tubes in direct line of sight of a flame at roughly 1,500 to 1,800 degrees Celsius. There is no film coefficient to correlate here. The tubes are heated by the fourth power law from flame and glowing refractory, and this section typically carries 60 to 80% of the total duty. Flue gas then passes over the bridge wall at roughly 800 to 1,000 degrees Celsius into the convection section, where fin tubes recover its sensible heat and preheat the incoming feed. Note the countercurrent arrangement. Cold feed enters the convection section and hot product leaves the radiant section. One variable limits the machine, tube skin temperature. The metal runs hotter than the fluid inside, and above the alloy rating it creeps and eventually ruptures, while coke laid down inside forces the skin hotter still. Two practical consequences follow from that crossover. The first is personnel protection. A surface hot enough to radiate strongly is hot enough to burn on contact, and radiant flux is also what makes standing near an open furnace door uncomfortable at a distance no convection could reach. Guarding, shielding, and time limits near hot surfaces are radiation problems. The second is money. A bare pipe at 200 degrees Celsius sheds roughly 1.9 kilowatts per square meter by radiation alone, every square meter of it, every hour, for the life of the plant, as fuel bought and burned. Insulation pays twice. It adds conductive resistance in series, and by presenting a cool outer surface, it collapses the fourth power term along with it. An insulated line, whose outer skin sits at 50 degrees Celsius, radiates about 136 watts per square meter, under a tenth of the bare figure. The economic thickness calculation of Chapter 5 counts both mechanisms. Anyone estimating losses from a hot line by convection alone is progressively more wrong the hotter the line runs. A hot surface both emits and absorbs, and only the difference matters. For the common case of a small object in large surroundings, meaning a pipe, a vessel, or a person enclosed by walls or sky so much larger that essentially none of the emitted radiation comes back, the net flux simplifies to Q equals epsilon sigma times T1 to the fourth minus T2 to the fourth, with T1 the surface and T2 the surroundings, both in Kelvin. Be honest about what that form assumes. It assumes the surface is gray, so its absorptivity equals its emissivity, which is Kirchhoff's law. That is a good approximation for oxidized industrial surfaces and a poor one for selective coatings and solar input. The small object assumption is doing real work too. It holds for a pipe in a large room and fails inside a furnace, where the object is a substantial part of its own enclosure. The general case needs the view factor, the dimensionless fraction of what one surface emits that lands on another. The simple two-surface formula is the special case where that fraction is effectively 1. Let us pull the chapter together. Radiation needs no medium. Every surface above absolute zero emits electromagnetic energy that crosses a vacuum, as sunlight demonstrates daily. Stefan Boltzmann gives E equals epsilon sigma T to the fourth with sigma of 5.67 times 10 to the minus 8 watts per square meter Kelvin to the fourth, so doubling absolute temperature multiplies emission by 16. A blackbody at 300 Kelvin emits 459 watts per square meter. At 1000 Kelvin, it emits 56,700, which is 123 times more for 3.3 times the temperature. Temperature must be absolute, Kelvin, and never Celsius. Emissivity runs 0 to 1, with oxidized steel about 0.8, refractory brick about 0.9, and polished aluminum about 0.05 as typical values, so low emissivity foil works as radiation insulation. Radiation reaches convection near 180 degrees Celsius on the H equals 10 basis, and dominates above about 500 to 600. Fired heaters split into a radiant section carrying 60 to 80% of duty and a convection section, with tube skin temperature the limit through creep and coking. Next chapter, heat transfer design and intensification. Welcome to the fifth and final chapter of our chemical engineering heat transfer series, heat transfer design and intensification, from single exchangers to the plant's heat economy. The first 4 chapters sized and analyzed one exchanger at a time. Today we zoom out, because a real plant runs dozens of them as a single connected system. Across these 10 slides, we will see how pinch targeting sets the duty that individual exchanger design must then deliver economically, meet the compact exchangers that make each match cheap and small, and mark the services where shell-end tube still wins. We will treat fouling as one more resistance in series and put a number on what it costs. We will monitor the overall coefficient as a soft sensor and turn cleaning into a scheduling problem. We will ask how small the equipment could be and why smaller equipment is inherently safer. Then we will look at the digital layer built on top of all of it, meet the thermodynamic floor that no software repeals, and close the series. Let us begin. Every previous chapter looked through a keyhole at one piece of equipment. Step back and the plant looks different. A refinery crude unit may carry 40 or more exchangers, and each one is a decision about which hot stream heats which cold stream. Those decisions are not made exchanger by exchanger. Pinch analysis, introduced in our Chemical Engineering Introduction series, computes the minimum hot and cold utility a set of streams can possibly need before any network is drawn. Its 3 golden rules follow: no heat across the pinch, no cold utility above it, no hot utility below it. Together they decide which matches are allowed to exist at all. That targeting stage sets the duty, but it does not build anything. Turning an allowed match into hardware is where this chapter lives, and the questions are relentlessly practical. How much surface, in what geometry, at what capital cost, surviving what fouling, and cleaned how often? Each match must be cheap, compact, and durable, and those 3 demands rarely point in the same direction. The shell-end tube exchanger of Chapter 2 is the industry's default, not its optimum. Its rival in clean liquid service is the plate-in frame exchanger, a stack of thin corrugated metal plates clamped in a frame, with hot and cold streams flowing in alternating narrow channels. 4 properties follow from that geometry. The corrugations trip the flow into turbulence at low Reynolds numbers, so the film coefficients of Chapter 1 are high without brutal pumping. Area density, the surface packed into a cubic meter of equipment, runs in the hundreds of square meters per cubic meter, against roughly 50 to 100 for shell-end tube, so the same duty arrives in a fraction of the floor space. The channel arrangement gives true countercurrent flow, so the correction factor F of Chapter 2 stays near 1 and approaches of 1 to 2 Kelvin are achievable where a shell-end tube unit would need 5 to 10. and the frame simply unbolts for cleaning. The limits are in the seals. Typical gasketed service caps out near 180 to 200 degrees Celsius and 20 to 25 bar. Compact does not mean better. It means better when the service allows it, and standard practice still sends large classes of service to shell-in tube. High pressures and high temperatures come first, because a gasketed plate unit is only as good as its elastomer, and those limits are hard. Heavily fouling streams come next. Coke and scale need mechanical cleaning, and rotting straight tubes through a removable head is routine, whereas coke in narrow plate channels may not be recoverable by chemical cleaning alone. Vacuum and condensing duties with large vapor volumes want the generous flow area a shell provides. And then there is the project argument that engineers underrate. Standardized mechanical codes and a century of fabrication experience shorten the schedule and lower the risk. Two relatives fill the niches in between. Spiral exchangers, two long channels coiled around a center, tolerate slurries and fibrous fluids because each stream has one unobstructed path. Plate fin blocks, usually brazed aluminum, reach extreme area density and tiny approaches in cryogenic duty such as air separation and liquefied natural gas. Fouling is the silent tax on every heat transfer design. Scale, coke, corrosion products, biofilm, and settled particulate build a layer on the wall, and Chapter 1 already tells us what a layer does. It adds a resistance in series. 1 over the fouled coefficient equals 1 over the clean coefficient plus the fouling resistance. Because the resistances add, the damage a given fouling resistance does depends entirely on how good the clean exchanger was. A superb coefficient has little resistance of its own, so a film dominates it quickly. A mediocre one barely notices. Put numbers on it. Take a clean overall coefficient of 600 watts per square meter per Kelvin and a fouling resistance of 5/10,000ths of a square meter Kelvin per watt. The fouled coefficient falls to 462, and at fixed area and fixed log mean temperature difference, the duty falls with it, a loss of 23%. Design responses come first, and velocity discipline is the strongest. Too slow and particulate settles and biofilm establishes. Too fast and erosion and pumping cost take over. Operationally, fouling is monitored rather than guessed at. Flows and 4 temperatures are measured on every serious exchanger anyway, so the overall coefficient can be back-computed continuously from routine instrumentation and trended over months. That is a textbook soft sensor from our chemical engineering introduction series. The quantity you want, the fouling state, is not measurable directly, so you infer it from cheap measurements you already have. Its failure modes are the usual ones. A drifting flow meter or a thermowell sitting in a stagnant pocket degrades the inferred coefficient exactly like real fouling does, so look for a step change against a gradual decline and cross-check against pressure drop, which rises as deposits narrow the channel. The trend then feeds a genuine optimization. Cleaning 2 often wastes production time and labor. Cleaning 2 rarely burns extra fuel and can force a throughput cut. The optimum sits where the marginal energy cost of one more day of fouling equals the daily amortized cost of the shutdown. That is a scheduling problem, not a judgment call. Process intensification asks a sharper question than how big must this be. It asks how small it could be. In heat transfer, the answers start from the lesson of Chapter 1. The smallest film coefficient dominates the overall coefficient, and on any gas-liquid exchanger, that is the gas side, often by 2 orders of magnitude. So put the extra surface where the resistance is. Fins, extended metal surfaces on the gas side, multiply the area facing the weak coefficient, which is why every air cooler, radiator, and air conditioning coil is finned on the air side and bare on the water side. Low-fin tubes carry short integral fins for moderate gains inside conventional shell-in tube bundles. A turbulator, a twisted strip or wire coil pushed inside a tube, swirls the flow to raise the tube side coefficient and pays in pressure drop. A heat pipe uses boiling and condensation inside a sealed tube to move heat with almost no temperature drop. and smaller equipment holds less inventory, which is a hazard reduced rather than controlled. Inherently safer design arriving as a side effect. An exchanger network is not a static object. Fouling accumulates on different streams at different rates, feeds change, ambient temperature swings, and a network optimal on the design day is merely acceptable a year later. The response is to re-rate the exchangers, recomputing what an existing unit actually achieves under today's conditions instead of trusting the duty printed on its datasheet, and to do that continuously rather than once at turnaround. That is a digital twin, a model kept aligned with the plant by live data, used to answer questions the instruments do not answer directly. Fed the soft-sensed coefficient of the previous slide, it estimates the fouling state of every unit, projects it forward, and prices the alternatives. On top of it sits optimization, which exchanger to clean at the next opportunity, how to split flow between parallel units, where to open a bypass. When each trial on a running plant is expensive or slow, the sample-efficient methods of our Bayesian optimization series are the right tool. But no model beats a log mean temperature difference of 0. That last point deserves a slide of its own, because it is the design tension of this entire series in one line. A twin can find the cleaning schedule and the best bypass split, but it cannot transfer heat across a 0 temperature difference, and it cannot recover the work destroyed when a 400°C stream heats a 50° one. That destruction is the entropy generation of our thermodynamics series, the minimum work argument wearing heat transfer clothing. Now hold that beside the economics. A tighter temperature approach saves energy every hour, and it demands area, because the required area is the duty divided by the overall coefficient times the log mean temperature difference. Push the driving force towards 0, and the area grows without bound, which is the wall chapter 2 put in front of us. So driving force costs area, and 0 driving force needs infinite area. Every exchanger you will ever specify sits somewhere on that trade, bought once in capital and paid for hourly in utility. Software optimizes within the floor, only the flowsheet moves the floor. 5 chapters, 1 sentence each. Chapter 1 built the overall coefficient from resistances in series and showed which one dominates. Chapter 2 turned that coefficient into hardware through Q equals U times the log mean temperature difference, and the exchanger configurations that make that mean temperature meaningful. Chapter 3 added phase change, the enormous coefficients of boiling and condensation, and the burnout and hazards that come with them. Chapter 4 introduced radiation and its fourth power law, which is why furnaces at high temperature are a different discipline from exchangers. Chapter 5 assembled all of it into networks, fought fouling, and shrank the equipment. The larger arc is the transport table. Flux equals coefficient times driving force, 3 times over. Momentum transfer is covered in our chemical engineering fluid mechanics series. Heat transfer is this one, driven by temperature difference. Mass transfer, driven by concentration difference, is a forthcoming series planned to complete the set. Where to go next? Chemical engineering introduction, chemical engineering thermodynamics, chemical engineering fluid mechanics, and process informatics introduction. Thank you for learning with us.